Hello. I'm finally back home. I was gone for like almost 3 weeks. I'm back home now, and we're gonna keep doing math. So, where were we? Wait, one sec. Okay, so last time we finished up until the end of question 9 in this section, and we're currently working on what is the last section of chapter 2. So yeah, I think the goal for today is to try and finish all the other questions in this section. Actually, there's a lot of them, so we may or may not be able to do that. We'll see. Yeah, that's kind of the goal for today. Be done with chapter 2. And as I had mentioned last time, I think 2 days ago, this chapter will hopefully help us learn more about the way subgroups of the group Sn are arranged in their subgroup lattice. And hopefully understanding this better will help us better understand the action of Sn on the collection of polynomials in n variables over a field. So that's what we're trying to work on or work towards, and hopefully understanding more about the lattice structure of Sn will get us closer to that goal. Wait, first I want to change the pen color. What should we change it to? Kind of thinking about a blue. We haven't done a blue in a while. Yeah, I like that. Okay, let's do this. Question 10. Classify groups of order 4 by proving that if a group has size 4, then either it's a cyclic group or it's the Klein 4 group. Okay, I see. How is that gonna happen with the lattice? I guess we should be able to figure this one out. So let's see. Let G be a group whose size is 4. So a group such that the size of it is 4. It has 4 elements in it. Then we need to classify how many such groups there are. The question claims there's only 2 of them. You're either a cyclic group, like this one, or you're a Klein 4 group. So let me just write down what those 2 groups look like. So again, I don't like the letter Z for cyclic because I don't think it makes sense. And it also gets confusing because there's other notation that also uses Z with a subscript. I think it's usually used for the p-adic integers. So yeah, I use the letter C because it's just better. It makes more sense. Cyclic, C for cyclic. So the cyclic group with 4 elements has the identity element, which we call 1. It's got some element which we're going to name G that acts as the generator of the group. And then every other element is just a power of this element G. And since the size of the group is 4, we ask that the generator has order 4, so that these are the only 4 elements that show up in the group. So yeah, this is one group. The other group of order 4 that we all know is the Klein group. So once again, this has the identity element, and then it's got 3 other elements, which I'm going to name A, B, and C, with the property that A, B, and C are all order 2, and if you multiply any 2 of them together, then you get the other one. So A times B gives you C, B times C gives you A, and A times C gives you B. So yeah, these are 2 groups that both have order 4. We want to show that if a group itself has order 4, then it has to be isomorphic. to one of these two. And given that this is, a question in the section on subgroup lattices, I'm guessing that's what we're going to have to do, right? So if we take a look at the subgroup lattice of C4, on top we've got C4, but in between that we've got the group generated by the element G squared, which has just got 1 and G squared. So this is a 2-element sized group living inside of C4. And then we've got the trivial group way down below. So this is the lattice structure for the subgroups of C4. Whereas on the other hand, if you look at the lattice structure of the subgroups of V4, well, then you've got 3 smaller subgroups living inside it. And each of them has order 2, and each of them contains the trivial group within it. So for example, this group here contains just 1 and A. Similarly, this group here contains just 1 and B, and so on and so forth. So these groups have a very different lattice structure. So I'm guessing if we can use, I don't know, some theorem to show that a group of order 4 has got to have either one subgroup of order 2 or 3 subgroups of order 2, kind of like this, then yeah, we'll be able to show that it has to be one of these 2 groups. So we know that the size of G is 4. So that means that if H is a subgroup of G, and let's say it's a proper subgroup such that H is itself not the identity group, which is to say that it's some group that shows up in between the topmost and bottommost layers of the lattice. So let's say we have some group like this, then the size of H cannot be anything but 2. So by Lagrange's theorem, any subgroup, the size of any subgroup divides the size of the original group. So since this guy has size 4, this guy can have size 1, 2, or 4, because those are the things that divide 4. But we've already ruled out the case where it's just the trivial group, which is the size 1 case. We've also ruled out the case where it's equal to G, which is the size 4 case. So the only option left is for H to have size 2. Okay. So we want to show that either there's just one subgroup of size 2, or that there is 3 subgroups of size 2, right? So we want to show that G is either isomorphic to C4 or that G is isomorphic to V4. So I always say this, whenever we want to prove an OR statement, one way of doing it is to suppose that one of them is not true and use that to prove the other one true. So if this can't happen, then this is the only other possibility. That's equivalent to just proving the OR statement, right? So suppose that G is not isomorphic to C4, right? Then we want to show that G, the only other option is for G to be isomorphic to V4. So G is not isomorphic to C4, which means that if H is any element inside the group that's not 1, if H is any non-1 element, then the order of H has to be 2. Once again, this follows because Lagrange says that the order of any element divides the size of the group. The group is size 4, and if there was an element of order 4, then that would be a generator, which would imply that G is isomorphic to C4. But that can't happen, because we assumed that it's not cyclic. So nothing can have order 4 Finally, we're also assuming that this element H is not 1, so it also doesn't have order 1. The only other option is for H to have order 2. And since G minus 1 is size 3, this means that there are 3 elements of order 2. Which means we're gonna get a subgroup lattice that looks like this. And so, G has no choice but to be isomorphic to V4. That's pretty nice. Okay. Let's keep going. Question 11. Consider a group of order 16 with this presentation. This is called the quasi-dihedral or the semi-dihedral group of size 16. Group has 3 subgroups of order 8. Okay. That's interesting. Right, so they're saying sigma on its own has order 8, and so it generates a size 8 subgroup, isomorphic to the cyclic group with 8 elements. Then tau together with sigma squared is isomorphic to D8, which makes sense. Tau kind of acts like the flip. Sigma squared acts like a 90-degree rotation. And what is this? Sigma squared and sigma tau together generate something isomorphic to the quaternion group, which is very weird. And every proper subgroup is contained in one of these 3 subgroups. Fill in the missing subgroups in the lattice of all subgroups of the quasi-dihedral group on the following page. I see. So we just need to fill in these blanks. That shouldn't be too hard. I'll just do it here on this page only. So it says, okay, look, here's 3 8-element subgroups. Now we just need to find the missing pieces living inside. So I kind of first want to write out the elements of the quasi-dihedral group with 16 elements. So what does that look like? Quasi-dihedral group with 16 elements. It's got an identity. It's got sigma and then all its powers. So up until sigma to the 7. We don't need to include sigma to the 8, because that's the same thing as 1 by definition. So powers beyond that are also again in this list, because sigma to the 9 is just sigma to the 8 times sigma, but this is just 1, and so this is all just sigma. So any higher power already is in this list. Okay, what else have we got? We've got tau, which has order 2, and we've got this weird commutation relation, but it means that we should be able to write every element kind of like this. So sigma tau, sigma squared tau, all the way up until sigma to the 7th tau. Yeah, looks pretty good to me. All right. So this subgroup here is simply this. It's a cyclic group, which means its subgroups are pretty easy to figure out. So for example, this guy is just going to be the group generated by sigma squared. So I wonder if I can zoom in here so that I can write smaller. So this is equal to the group generated by sigma squared. Okay, there. What else? We've got the group generated by sigma 4 here. And then this group lives inside here, does it? Yeah, it does. It also lives inside here. Okay, so right, inside this is this group, inside which is this, and something else. So let's try and figure out what this something else is by first figuring out what this group looks like. So we're generated by sigma to the 4 and tau. So what can we write as a product of these guys? There's 1, there's sigma 4. Another power of sigma 4 up just brings you to sigma 8, which is just 1. So as far as sigma to the 4's powers are concerned, this is the only one there. Then there's tau, and similarly tau also has order 2. So it's seeming to me like this is going to be, again, isomorphic to this guy over here. It actually, it has this lattice structure of its own, right? With the 3 subgroups, all of size 2, just as we saw over here. So if we can figure out, there's sigma to the 4th, there's tau, which means what's left is their product. So sigma to the 4 tau, which is also an order 2 element, which means that this guy is equivalent to, I guess it doesn't scale my pen size down. This is equal to sigma to the 4 tau. All right. What else? I guess let's check out what this group looks like so we can figure out what this should be. Yeah, because we need to figure out what this is before we can figure out what this is. So interestingly, this guy also has a similar 3 subgroups, all of the same size inside here. And here the elements seem to be tau sigma squared, sigma to the 4. Does this have order 2? So that's an interesting question. Let's find out. So we've got tau sigma squared, so it's just tau sigma squared, tau sigma squared. And then in the group presentation, we were shown the cost of swapping a sigma with a tau. So let's see. We can swap these two a couple of times and essentially get tau squared, because this one comes here. And then the 2 sigma squares move to the other side, each becoming a sigma cubed. So in total, there should be sigma 6 and then another sigma here. So sigma to the 8. Sigma to the 8 is 1, tau to the 8 is 1, so this just comes out to 1. So tau sigma squared itself has order 2. It's pretty cool. I'm curious, what happens when we swap these two? So more importantly, what happens when we swap these two? This is the same thing as tau sigma to the 6, which is the same thing as tau sigma squared, sigma negative 2. I don't know. Doesn't seem to be, which kind of bothers me because I was under the impression that this, and whatever this is, would form another version of the dihedral group, but it doesn't seem to be that way. I just need to make sure, right? Like, let's also check it out here. Like, we saw what happens when you multiply it in this order. What happens if you swap them, right? So what is tau sigma to the 4th? So let's see. We can take 3 of these sigmas and swap them over here for 1 sigma. So sigma tau sigma. The question is, does this swap in the same way? I don't know. I want to send this tau over there, right? So let's let's do an experiment, I guess, first. We know how to swap sigma and tau when they're in this order. It's the same thing as tau sigma cubed. But what happens if the tau and sigma are in this order? Is there another better, can we swap them analogously? Let's find out. Maybe we can use the fact that tau has order 2. Right? Tau has order 2. Which means it's the same thing as tau cubed sigma. But I don't know that this is doing anything, really. What happens actually if we multiply by tau squared on the right hand side? Because this is like multiplying by 1, so it doesn't really change anything. Now we can swap these using this rule. Right, so if we do that one at a time, we get something that looks like this. These cancel out, and we're left with sigma cubed tau. So yeah, you can swap these in exactly an analogous way, which is good to know. So if tau sigma to the 4, now I want to check essentially if sigma to the 4 tau is the same thing as tau sigma to the 4, right? So we know that tau sigma to the 4 we should be able to swap them analogously. 4 times 3 is 12, so this turns into sigma to the 12 times tau. But sigma has order 8, so this is the same thing as sigma to the 4 tau. Alright, that's pretty nice. So it really is isomorphic to the Klein 4 group. So this is, I guess, an important reason why there are only these 4 elements. If this was different from this, then this would be a new, different element inside this group, which would not be that good. Alright. Yeah, so where are we now? Right, we wanted to figure out what this is, which is completely blocked, so let me bring that back. Yeah, let's look at the group generated by sigma squared and tau. What does this group contain? It contains one, it's got sigma squared and then all of its powers. So there's sigma to the 4, sigma to the 6, and then there's, tau, sigma squared tau, sigma to the 4th tau, and sigma to the 6th tau as well. And I also should make sure that tau times sigma squared and all the reverse versions of these are already in here, right? So if we take a look at this, we can swap these two and get sigma to the 6 tau. So if we swap these, we just end up getting this. And similarly, if we swap these, we would probably end up getting this. And we already saw back here that if you swap the order of this, it just comes back to equal itself. So this is it. These are the only elements in this group. Okay, we've identified a couple of subgroups. One of them is the group generated by... I am confused. Because this is an 8-element group. What do we know about it? One subgroup is the one generated by this. One other subgroup is the one generated by tau sigma squared, which is this guy here. Right? Because these 4 are all order 2 elements, at least I think, right? Let's say we have sigma to the I tau. If we raise this to the power 2, this is sigma to the I tau, sigma to the I tau. And then we can swap these two, and it comes out to sigma to the I plus 3i because swapping them, comes at the cost of multiplying the power by 3. And then 2 taus. But 2 taus are just 1, so we can kind of get rid of that. And so this is really sigma to the 4i. I see. So this guy only has order 2 if I is itself a multiple of 2. So this is the difference between the quasi-dihedral and the actual dihedral group. In the actual dihedral group, which we typically write as generated by R and S, where R kind of works like this, like sigma does here, and S kind of works the way tau seems to work here. There, R to the I S squared is always 1. But here, sigma to the I tau squared is 1 only if I is a multiple of 2. Which makes sense, I guess, that there should be this kind of a difference. So, in this case, all the i's here are multiples of 2. So, these guys really are all order 2 elements. And we can even verify that, right? Like, let's take sigma squared tau. When we swap these, we get sigma squared plus 6 tau squared, which is just 1 because this is sigma to the 8 and this is tau to the 2. And then similarly, sigma 4 tau is sigma 4 plus 12 tau squared, which is sigma to the 16, which is just 1 squared, and then tau squared, which is just 1. So even this is 1. And instead of 4s, if we just did 6s, so sigma 6 tau, then this comes out to sigma 6 plus 18 tau squared, which is sigma to the 24, which should just be 1 cubed. And then tau squared is also 1, so this is just 1. Okay. I do want to see what happens when you multiply these two together. Right, so sigma squared tau times sigma 4 tau. We can do the swap again, and we get sigma squared, or sigma to the 2 plus 12 times tau squared, which comes out to sigma to the 14, which is the same thing as sigma to the 6. So multiplying these two actually gives you this. So that's why 1 and then these 3 together don't make a subgroup. Okay. Interesting. This is a weird group. I'm not feeling familiar with it. I feel like at this point the dihedral groups have become really familiar for me. But this quasi-dihedral bullshit is kind of weird. So here's sigma squared tau. It's got this as a subgroup, sigma 4 tau. So what is this? Clearly this is something that contains, maybe, right? The question is, what is the join of these two? So that's an interesting question. It actually should be, though, the join of these 3, which is annoying because I don't yet know what this is supposed to be. So let's figure out. Let's look at the group generated by tau sigma squared and sigma to the 4. So this should live inside here. And it's got 1. It's got tau sigma squared, which I would prefer really to write as sigma 6 to the tau, in keeping with my prior notation. And sigma to the 4. But first off, this is already order 2. So it's not really doing a whole lot there. Then there's sigma to the 4, which is also order 2. And what happens when you multiply these two things together? Well, you could do it in a couple different orders, right? You could do sigma 4, sigma 6, so really it's sigma 10 tau, which is the same thing as sigma squared tau. Okay. Interesting. What happens if you swap the order? So this time we do sigma to the 6 tau, sigma to the 4. Well, this time we get sigma to the 6 plus 12 tau, which comes out to sigma to the 18 tau, which is the same thing as sigma squared tau. So swapping these two in multiplication doesn't matter, you always get sigma squared tau. So this is another group isomorphic to the Klein 4 group. 3 order 2 elements, such that when you multiply 2 of them, you get the other one. Like that. Alright, so I believe that should be what this is. So this is the group generated by tau sigma squared and sigma to the 4th. Here's the stuff generated by, so that means this has to be the one left over, right? Tau sigma squared is really the same thing as sigma 6 tau. So this corresponds to this up here. This corresponds to this here. And that means what's left here corresponds to sigma squared tau. Nice. Wait, didn't I also write down what this was? What was this? This was the other one. Sigma 4 tau. Like that. And now we need to figure out these two, and we'll be done. Okay. So what is sigma squared tau sigma? What have you got? So we've got 1, we've got sigma squared and all of its powers. And then we've got tau sigma, which once again I would rather flip and write as sigma cubed tau. And then we've got all these multiples, so sigma to the 5 tau, sigma to the 7 tau, and then also sigma tau itself. Okay, so it's kind of similar in structure to this group, except over here, all the sigmas had even powers attached to the taus, whereas here all the sigmas attached to the taus have odd powers. So it feels very, very similar, at least to me. And it definitely feels like the subgroups are not as complicated as they were here, which is kind of weird. I wonder why that is. I guess we'll find out. So we need to find out what the other two subgroups of this are, apart from sigma squared, apart from just this stuff together. So let's see. What is the group here generated by sigma cubed tau? What does that look like? As I said, it's got sigma cubed tau, it's got the identity, it's got this thing squared. Sigma cubed tau squared looks like this. Comes out to sigma 3 plus, not 12, plus 9 tau. Which comes out to sigma 12 tau, but 12 is 4 more than 8, so this is sigma to the 4th tau, which is very concerning because what? Apparently, this group has order 8 and is isomorphic to the quaternions. So apparently sigma tau has order 4. Which is making sense to me. But man, this is weird. Because... yeah, this is actually very confusing. Sigma... so weird. Here they wrote down sigma tau, but here they have tau sigma? Is this even isomorphic to the quaternions? Weird. So here, sigma square is kind of playing the role of -1. And if this is I... no, I guess sigma to the... or sigma... what? Sigma square is I. Sigma to the 4 is -1, kind of. I see. So let's do this in a more interesting way. Yeah, why is this isomorphic to the quaternions? I am not seeing this. And it's very suspicious to me that the order of this changed to this. Why is that happening? I feel like that should not be happening. Huh. Okay, I think I need to be a little bit more careful when looking at this group. I don't think it's this clear cut. Certainly this is all in the group because we've got sigma squared. Certainly this is in the group. So let's start with that, right? And let's maybe keep it in the tau sigma ordering. We've got tau sigma. We've got tau sigma squared. So that looks like this. But we can swap these two. Actually, you know what? Let's swap these two. And get tau squared sigma to the 4. I see. So this guy's powers just come out to sigma to the 4. Okay. And let's also verify that, you know, sigma cubed tau squared is also sigma to the 4. Once again, we swap these two middle ones. What do we get? We get sigma to the 12 tau squared, which really is sigma to the 4th. Okay. That's less worrying. What else have we got? Well, clearly we've got tau sigma cubed. Okay. What do you have to say of tau sigma cubed? What happens if we square u? So tau sigma cubed times tau sigma cubed. What is this? If we swap these two, we get tau squared sigma to the 12, which once again is sigma to the 4. Interesting. So it's like this is -1. It's like this is I. This is -I. This is J. This is K. What about tau sigma to the 5th? So tau sigma to the 5th times tau sigma to the 5th. What are you? If we swap the middle two, we get tau squared times sigma to the 20. Which is... 20 is a multiple of 4, but not 8. So this is also sigma to the 4th. And this is sigma to the 4th times this guy. So it's like -j. I should verify that multiplying by sigma 4 on the left and right doesn't change anything. So let's take a look at sigma to the 4 tau sigma. We can swap these two and get sigma to the 7 tau, which is, oh, we want it in this form, right? So I guess now we swap again and get tau to the sigma to the 3 times 7, which is 21. 21 is in fact 5 more than a multiple of 8, and so this is sigma to the 5. So the order doesn't really matter, which is good to know. And then the last thing, which is going to be tau sigma to the 7, should be minus k. Okay, so that's why this is isomorphic to the quaternion group, because you can write it like this. Okay. So what are the subgroups of the quaternions? It can be generated by -1. Wait, I want to find the quaternion situation here. You have 3 things generated by I, j, and k respectively. Oh, fuck. I messed this up a little, didn't I? Yeah. This should be I. This should be -1. There we go. Now it's making more sense. Because now if you look at this thing over here, this is like I. So this is I. And then we're supposed to have a j and a k. And look, here's -1. Okay, so what is j? J was sigma or tau sigma. This is the same thing as tau sigma. And then this here is going to be the same thing as k, which is tau sigma cubed. And they each contain -1, which in this setting is called sigma to the 4. And I believe this is it. So it's interesting, like we're noticing now how this group, if you can figure out what its top layer is, and you already know the lattices for the top layer, you can kind of cross-check G's lattice by seeing whether whether the lattices of these 3 respectively are coming out as sublattices in the way we want them to, right? Because this one is like D8, and so if you just look at everything you can reach by going downwards from here, so you know, all of this stuff, you really do get something that looks identical to D8's lattice, which is pretty cool. On the other hand, if instead of this stuff, we looked at the stuff underneath this directly, we notice that, look, the group generated by this is isomorphic to the cyclic group with 8 elements. In other words, Z mod 8Z. And we saw that whenever you have Z mod P to the n Z, where P to the n is some power of a prime number, just like 8 is actually 2 to the 3, then you're gonna get a lattice that looks like this, like a straight line. And that's why down here you have this straight line lattice as far as sigma is concerned. And then similarly, here we have a mirrored version of the quaternion's lattice over here, because this group is isomorphic to Q8. Of course, you know, the unique way in which these lattices kind of overlap, like this line here is common to this guy's lattice, and this guy's lattice. That is because of the way these 3 groups are arranged together within here. So, pretty cool. All right. Let's do question 12. The group, this guy, has order 8. This kind of feels like the semi-dihedral group. Similar-ish at least. Has order 8 and has 3 subgroups of order 4. Every proper subgroup is contained in one of these 3. Draw the lattice of all subgroups of A, giving each subgroup in terms of at most 2 generators. So, okay, let's draw A up top. Actually, let me first write out what A really even is so that we know what we're working with. So A is generated by 2 elements called A and B, where A has order 2, B has order 4, and there's this kind of anti-commutativity relation between them. Oh no, A and B commute, right? Yeah, so they commute. Alright, so if we were to write this out as a set, it's got 1, it's got A and its next power, which comes out to 1. So let me start with B actually. So here's all the powers of B. Then there's A, and then everything you get when you multiply B's with A's. So BA, B squared A, and B cubed A. And since A and B commute, if you swap these, you get the same element. If you swap these two, you also get the same element. Similarly, if you swap these. So we can just choose to write everything with a B in front of all the A's, because at the end of the day, it doesn't matter. It's the same thing if you swap the B and the A. Okay, so that's what this group looks like. It's got 3 subgroups of order 4. So let's put those up top. The order 4 subgroups are A and B squared, which should be isomorphic to the Klein group. What else have we got? We've got the thing generated by B, and we've got the thing generated by AB. Okay. So we've got this. Now this guy is a Klein 4 group, which means it's gonna have 3 subgroups, each of size 2. So let's put all the size 2 subgroups on this line here. So there's gonna be something generated by B squared. There's gonna be something generated by A. Actually, let's put the B squared one over here because it's also contained in here. I believe it might also be contained in here, right? Because AB squared comes out to A squared B squared. Again, because A and B commute. But A squared cancels out to 1. And so B squared really is also inside here. Okay, what else? We've got the group generated by A. So we can leave that one over here. And then there's one more generated by AB squared. Down here is the trivial group. This, and this. B was a cyclic group, so its lattice looks like this, and we're done with that. AB is another cyclic group, so its lattice is also going to look like this, and we should be done. Pretty sure. I'm pretty sure this is it. Yeah, this makes sense. Okay, let's keep going. This is kind of annoying. We can't see the question numbers. Might have to make this a little smaller so it all fits. Okay, I think that's better. Okay, where were we? Question 13. The group G looks like this. Okay, once again, very similar to the dihedral group, except the 2 generators commute instead of the anti-commutative commutativity relation that we have in dihedral groups. This is order 16, has 3 subgroups of order 8. It's this guy. There's this guy. There's this guy. Okay. So we just need to draw the lattice again. So this time G is generated by x and y, where x squared equals y to the 8 equals 1, and xy equals yx. So what is happening here? So way up top we've got G, and we've got 3 subgroups of order 8. Every proper subgroup is contained in one of these 3, which means that these make mark the top row. We've got x, the group generated by x and y squared. You've got the group generated just by y, and you've got the group generated by x, y. So let's try writing this out as a set. We've got 1, we've got y squared, y cubed, y to the 4, 5, 6, and 7. And then you've got x, yx, y squared x, so on and so forth, up until y to the 7th x. 16 elements. Now the group generated by x and y squared, right? So if we look at this guy, what do we have? We've got 1, got y squared, y to the 4, y to the 6, and we've got x, y squared x, y to the 4x, y to the 6x, and I believe that should be all. Now the group generated by y squared should live inside here as well, so let's put that there. Before that, I just want to move this down a little to make some space. So let's put the group generated by y to the 4 here, and just for continuity we'll put the group generated by y to the what? I guess the group generated by y to the 8 is the trivial group, right? So something like this. I guess, wait, this should be a y squared, then a y to the 4, and then the trivial group. So something like this. Yeah, that's better. And we also have containment this way. What about xy? What happens when you square xy? You get x squared y squared, again because they commute. But x squared is 1, so this is just y squared. And then when you multiply by another xy, you get y. Okay. So if we write out xy, this has got 1, then it's got xy, then it's got y squared, then it's got xy to the 4. No, xy cubed, sorry. Then it's got y to the 4, xy to the 5th, y to the 6th, xy to the 7th, and I think that's it, right? 1, 2, 3, 4, 5, 6, 7, 8 elements, and it's cyclic. So inside we've got the group generated by y squared, which is these, and then inside that we've got the group generated by y to the 4, which is just this. So as far as xy is concerned, we finished its lattice. As far as y is concerned, we finished its lattice. So this is the only guy that we still need to worry about. Okay. Did we see this group anywhere? Sorry, I guess this group anywhere. I guess that was this, right? So now we should see this lattice repeating itself over here. We might have to do things a little bit carefully. Let's see. So it's got the group generated by y squared. That's cyclic. There should be another cyclic group in here somewhere. I'm thinking this guy, right? So if you look at the group generated by y squared x, if this has size 4, then we'll be doing well. So this has got 1, it's got y squared x. The next power of y squared x should be y4x squared, which is just y to the 4. Then comes y to the 6x, and that's it. So this is also a cyclic group. So I'm going to stick it over here, y squared x, and then put this here and put this here. There, I think that works. Just want my lines to be better. Okay. What else did we have last time? We had 2 cyclic groups and then 1 Klein-Ford group, right? So what's the order 2 element here? X. So I'm guessing the next group we need to look at is the one generated by x and y to the 4. Let's see. X and y to the 4. What do you generate? You've got 1. You've got y to the 4. You've got x. And then you've got y to the 4 x. So look, this really is isomorphic to V4, the Klein group. Because multiplying any two of them gives you the other one. Multiplying these two gives you this. Multiplying these two gives you this. So over here, we've got x with y to the 4. Like that. And that was a Klein-Ford group, which means it itself is going to have 3 subgroups. So one of them is this. Then there's one generated by x times y to the 4th, which lives here, and then here. And there's the group generated by x, which goes like this. And I believe this should be the lattice. I'm pretty sure we're done. Yeah, this looks right to me. I'm actually really enjoying computing these lattices. I don't know why, but it's kind of pleasant. Okay, question 14. Let M be the group of order 16 with the following presentation. This is called the modular group. Once again, an order 2 element, an order 8 element, but this is the commutation relation. This is called the modular group of order 16. It's got 3 subgroups of order 8. Show that the lattice of subgroups of M is the same as the lattice of subgroups of Z mod 2 cross Z mod 8, as in the one from the previous question, but that these two groups are not isomorphic. Okay, so this question is answering a question that I had, which was, if two groups are isomorphic, or I guess, do two groups have the same lattice structure? If and only if they're isomorphic? According to this question, no. You might have isomorphic groups whose lattices... Oh no, you might have non-isomorphic groups that have the same lattice. It's kind of weird. So let's write this out and compute its lattice. So here's M. It's generated by U and V, where U squared equals V to the 8 equals 1, and VU equals UV to the 5th. So first off, I want to figure out whether we can swap U and V in the same way as we swap V and U. So what is this? Let's multiply by a U square on the right. Because U square is 1, so it doesn't change anything. Uvu. And then we swap these twice. So get U cubed times V to the 10. Now U cubed is just U. V to the 10 is just V squared. What? No. That's very concerning. How did that happen? How did we swap these two? Wait, I gotta think. Oh, I hate these new groups. Okay. Let's think. UV equals UVU squared. And then we swap these two, because we know how to swap them. So let's do this one step at a time, right? We first swap the VU here, and we get a UV to the 5th with another U at the end. I see. Actually, I don't. Yeah, I do see actually. So this is what? U squared V to the 5th U. And then swapping these, you have to send V over here 5 times. So it's U cubed times V to the 25. Should be the same thing as U, and then V is order 8, which means this is UV. God damn it, that didn't help me at all. I knew already that this was UV. Right, so what do I want to do? I want to bring V to the left-hand side. How do I do that? I know. UV is the same thing as U to the 5V because I've multiplied on the left by U squared, but U squared is 1. So these two are the same. Okay, and now, no, I still can't swap very nicely. Very weird. What if I multiply by a V to the 8 on the right? So UV to the 9. Now we can use this to swap this way. So we take 5 of those V's and convert it into a VU, and then there should be 4 of them left. Okay, how do I bring these V's all the way here? Yeah, I'm confused because we want our V's on the left. Yeah, I'm feeling stuck now. There has to be a way of swapping these the other way around as well, right? How do we swap these? Okay, let's try UV U squared again. And then this turns into U squared V to the 5th U, which turns into U cubed V to the 25th. Which is the same thing as UV again, right? This hadn't worked the first time. But what happens if we up the stakes and multiply by a U to the 4 this time? And then we have to swap all of these. So putting a V here comes at the cost of multiplying multiplying the power by 5. But we're doing that 4 times. So it's going to be U to the 5 times V to the 5 to the 4. I think. I'm not fully sure actually. Let's do this one at a time. This becomes U squared V to the 5th U cubed. And when we do it again, it becomes U cubed V to the 25 to the U squared. Now V to the 25 is just V. This is U cubed V U squared. And then we swap once more. We get U to the 4 V to the 5 U. And in the end, we just get U to the 5 V to the 25, which is still UV. Doesn't help. How the what? How do I use this identity? Because what I'm trying to prove is this is the same thing as v to the 5u. The same way this, it's like the analogous swap. How do we do that? Maybe we start with v to the 5u and then use this identity a bunch of times. Yeah, maybe that'll work actually. So v to the 5u swaps into v to the 4 times u v to the 5. Right, so this when we swap the whole thing is going to be uv to the 25, which is uv. That's clever actually. So if we wanted to really do this backwards, the morally correct way, we would say, look, uv is really the same thing as uv to the 25. Then we can swap these back, and it becomes vu. Yeah, like you have to bring 5 copies of v5 across, and each time you do so, a v5 turns into a v. So in total, it's just vu. No, it's v to the 5u. Sorry. Yeah. Okay. That's good. I'm glad we figured that one out. Now it's got this as a subgroup. Which should look just like this. Right, so in question 12 we had this lattice. So let's make sure we know, or I guess rather, let's look at this group, uv squared. We need to show it's isomorphic to this group that we saw in question 12, right? So let's look at the group generated by u and v squared. So this as a set, it's got 1, it's got v squared, it's got v to the 4, it's got v to the 6, it's got u, it's got v squared u, it's got v to the cubed u, v to the 5u. Wait, what am I doing? No, it's got v to the 4u, v to the 6u, and that should be all. Now, we need to make sure that, swapping these orders doesn't take you out of the group. So let's say we had uv squared. What does that come out to? Well, we know we can swap them like this. So it should come out to v to the 10u, which is just v squared u. So swapping the order brings you back here. That's interesting. So u and v squared commute apparently. Weird. What about uv to the 4? What happens now? Well, now it becomes v to the 20u, which should be v to the 4u. So swapping these two brings you back here as well. Similarly, uv6, I'm sure will do the same thing and just be the same thing as v6 to the u. So this time when we swap, it turns into v raised to the 30 times u. What's happening here? Right, and v to the 30 mod 8 is v to the 6u. There we go. Alright, so we figured out what uv squared looks like as a group. Now let's go and remind ourselves what the group in question 12 was. Group in question 12 looked kind of like this. So what's the order 2 element? I'm guessing the order 2 element is this guy here. Or rather this guy here actually. Yeah. So if you look at this, really it's generated by u, it's generated by v squared, where u has order 2, v squared has order 4, and uv squared is actually the same thing as v squared u. We just verified this. So it really has the same presentation, which makes this isomorphic to C2 cross C4. Okay, so if we now try writing out M's lattice structure, here's M. Inside it, we've got the group generated by U and V squared. What else did the question say we have? We have the group generated by V, which is cyclic, which makes sense because V is an order 8 element. And then we've got UV, which should also generate a cyclic group. So let's just look at the powers of UV. So the group generated by UV contains the identity, it contains UV, then it contains weird. UV squared is going to be UV. We can swap the middle two, and that turns into U squared V to the 6. U squared is 1, so we get V to the 6 this time. Okay. Yeah, this is so weird, dude. So weird. Why are we going straight to V to the 6? I'm guessing next step, so when we do UV cubed, so this should be U squared V to the 6 times UV. Now we can swap these and get U cubed times V to the 31, which is U times V what? V7, I guess? That's just awful. I don't like that. Yeah, no, that's not seeming right to me. Mod 8, 31 is 7 mod 8. It's 7 more than a multiple of 8. That's why this, right? Did I do this part correctly? You know what? I can actually do this in a slightly simpler way. Say this is U squared V times UV squared. And then swap these again. Which turns into U cubed times V to the 7. So I was right. It really is U cubed V to the 7. So next up is U cubed V to the 7. This is a really weird cyclic group, I have to say. I do not at all like it. Okay, let's look at UV to the 4th, which should be U cubed V to the 7 times UV. And what are U? I guess we have to swap these. Or really swap 5 of these first, right? So we've got U cubed V squared UV squared. Yeah. And then we swap these again and get U cubed. Really U to the 4. V to the 12. Now U has order 2 and V has order 8. So this is just V to the 4. Now when we take it to the 5th power, what happens? This should be just V to the 4 times UV. And we can swap these two. I guess we wanted to put U in front, right? We should be swapping these. So we get U V to the 21, which is U V to the 5. I'm pretty sure. Right? Yeah, 21 is 5 more than a multiple of 8. Did I do this swap correctly? There's 4 V's. Each time you bring it across, you get 5 of them on the right hand side. So 4 times 5 is 20, so these turn into 20 V's on the right. So in total there's 21 of them. 21 is 5 more than a multiple of 8. You know, it's 5 more than 16. So yeah, this works. This is actually, even here, the U cubed, you can just turn it into a U. I see. So this is a little less complicated now. Now I'm sure the next is going to be V squared. So if we do UV raised to the power of 6, this should be UV to the 5 times UV. And we can swap these and just get U squared V squared, which is V squared. And lastly, UV to the 7th power is going to be V squared times UV, which is, we can swap these and get UV to the 11, which is UV cubed. And we can also check UV to the 8, which should be UV cubed times UV. Swap these two, get U squared V to the 16, which is 1. So that's it. Cyclic group of order 8. That looks horrible. Honestly, a really weird group. Really, really weird group. It might have been nicer if they started with this. They used this as the generator, but you know what? Whatever. Doesn't matter. So this is what UV looks like. I'm gonna stick it, I don't know, here. Here seems good. And then make a line here to show that, look, this is part of this question. So far, we've got this much of the lattice. Now V is cyclic, which means it's got a very nice structure, like this. Finally V8. I guess V8 is just the trivial group, so like this. Now UV squared looks kind of like this group from question 12, so let's just remember what this lattice was. So, and where here A was the order 2 element. So here's UV squared. Inside this, we're gonna have U and V to the 4. And we're gonna have just U and then just V squared, which is already there. So let me space this out a little better. So here's U, and here's U, V to the 4. So something like this. Right, it had 3 things. This one was cyclic. This one was also cyclic. So like this. And we can verify that U squared really is the same thing as V to the 4. Although I'm actually really suspicious about that. Isn't U squared just 1? I see. Oh, it's these 3. I see. I thought we were looking at this group. We're actually looking at this group. That makes sense. So this is the group generated by A and B and its subgroups. It's got 3 subgroups. One generated by A and B squared, which is U and V to the 4. Then we've got B here, which should be V squared here. And then you've also got the group generated by UV. No, you've got the group generated by uv squared. So let's take a look at the group generated by uv squared and just verify that this is cyclic of order 4. It's got 1, it's got uv squared. Now when you square uv squared, and swap these two, you get u squared v to the 12, which is v to the 4. So next up, v to the 4, and then v to the 4 times uv squared. I guess we want to swap these, right? So u v to the 22, which should be v to the u times v to the 6. So next up is u times v to the 6. And finally, we're going to have v8, which is 1. So we get that. Okay, so that's reassuring. This lives inside this. And now inside the uv piece, just here, there's 3 subgroups of its own, generated by the product, and then the 2 things separately, because this is isomorphic to the client 4 group. There we go. So we've got v4 over there, we've got uv4 over here, we've got u over here. So like this. Okay, and then uv was a cyclic group that contained v square in it, see? And yeah, I believe this is the structure. And if you take a look at this and compare it with this, what do we notice? We've got 3 things up here. The one on the left has 3 things below it. The first of those has 3 things below it. The second of those cyclic, and third also cyclic, which is the case here and here. So yeah, these 2 lattices, this lattice is the same in structure as this lattice, even though M and G are not isomorphic. So how do we verify that M and G are actually not isomorphic? Right, so if we write this as a set, M has got 1, the powers of V, and then it's got U, and then V, the powers of V times U. Would there be a way of sending these elements to these elements in a way that, you know, makes the relations work out? So here the 2 generators commuted, and one had order 2 and one had order 8. So here the only order 8 elements are v cubed, v to the 5th, and v to the 7th. The order 2 elements are u. Which else were the order 2 elements? I guess the order 2 elements will be all of these guys. The order 2 elements were u, uv to the 4, and v to the 4. So is there a pair of elements from here, one from here and one from here, such that they commute? We know that v and u don't commute. Oops. Yeah, we know that v and u don't commute. What about v cubed and u to the 4? So uv to the 4 times v cubed is uv to the 7. Is this the same thing as if you do it the other way around? So v cubed uv to the 4. Well, this stuff here, if we swap these, I guess we want to swap these 2. You get uv to the 15 plus 4, so 19, which is u times v cubed, which is definitely not the same. Okay, so these 2 don't commute. Yeah, there's a lot of pairs to check here. VU, yeah, and I'm sure if one checks all these pairs, we'd be able to prove this. I don't want to do that, so I'm just gonna say it works and keep going. We're done. Okay, question 15. So what's going on here? Describe the isomorphism type of each of the three subgroups of D16 of order 8. So let's go back to the lattice for D16. It looks like this. It has these three subgroups. So this is isomorphic to C8. It's a cyclic group with order 8. What about this? And what about this? So the group generated by S and R squared, what does it have? It's got 1. It's got R squared, R to the 4, R to the 6. It's got S. It's got R squared S, R to the 4S, R to the 6S. My hypothesis is that this is isomorphic to D8. How do we check this? Well, we can write this as SR, R squared, sorry, where R squared to the 4 equals S squared equals 1. And is it the case that SR squared is the same thing as R negative 2S? If this is the case, then this is isomorphic to D8. So is this the case? Well, according to D16's relation, it is in fact true. So yeah, this is isomorphic to D8. What about this guy? The group generated by SR and R squared. I think it's just another copy of D8. Yeah, this lattice also looks this guy's lattice also looks the same as this guy's lattice. I just want to verify that they are really the same group. So we can write this again as generated by two generators, where R squared to the 4 is the same thing as SR squared is 1. Now, is it the case that R squared SR is the same thing as SR times R negative 2, which would be SR inverse? Are these the same? Well, according to the way D16's relation works, swapping this turns into S R negative 2R. Which, yeah, it really is. It works. It totally works. So yeah, that's also D8. Isomorphic to D8. That's pretty nice. So D16 has two copies of D8 living within it. It's good to know. I wonder what happens, for example, in D14. I might try computing that lattice just for fun. But yeah, let's see. Question 15. So we did question 15. Let's just keep going on to question 16 because I did it in the book itself. Question 16. Use the lattice of subgroups of the quasi-dihedral group of order 16 to show that every element of order 2 is contained inside this proper subgroup. Okay. Well, here's the lattice of the quasi-dihedral group, right? Yeah, here we are. Quasi-dihedral group. Now the order 2 elements are these guys. And where did we want it to show they were all living in? They all live in tau and sigma squared. Tau and sigma squared is up here. All of these things do in fact live in here. So question 16 is proof by picture. I'm not even going to write a picture. The lattice makes it evident. So let's keep going. Question 17. I guess this is why the lattice is so useful. So many properties of the group are captured by the lattice, which is quite nice. Use the lattice of subgroups of the modular group of order 16. Show that the set of order 2 elements or I guess the 2 torsion elements is a subgroup of M isomorphic to the Klein 4 group. So which one was the modular group? This is question 14. So over here. So all the elements such that x squared equals 1 is a subgroup isomorphic to the Klein 4 group. Now here's the order 2 elements. But the order 2 elements are the only ones to satisfy this equation. Any smaller order will also satisfy this equation. So for example, this guy, 1, also satisfies that. So what's the group that contains all 3 of these? Well, it's this right here. So yeah, we already discussed how this was isomorphic to V4. So I'm gonna leave that as a proof by picture as well. Let's keep going. Question 18. Use the lattice to help find the centralizer of every element of the quasi-dihedral group of order 16. So here's the quasi-dihedral group of order 16. We want to find the centralizer for every element. I hate that. I don't want to do that. So at some point FAST64 had suggested that, and I guess I erased it, but let me write this proof down here. So let G a group, then and let A and B be inside this group. So A and B are 2 elements. Then we want to show that the centralizer of this group here is the same thing as the intersections of the centralizer of each element. So it's really enough to find the centralizers for each element if you want to figure out the centralizer of some larger group. At least as long as that larger group is finitely generated. I don't know if this still works if you use an infinite set in here, but we'll see. And the proof of this is let R be inside the centralizer of here, right? That means R commutes with everything inside here. Then this means in particular that RA equals AR and that RB equals BR, which means that R is in fact in the centralizer of A and that R is inside the centralizer of B as well. Okay, what about the reverse direction? So let R be inside the centralizer of A and also in the centralizer of B. This means that R commutes with A and that R commutes with B. But does it commute with an arbitrary element in here? Well, let's take an arbitrary element. The group may be non-abelian, right? So let's see, how do I write this? Let's say we have A to the E1, B to the F1, A to the E2, B to the F2, so on and so forth. A to the EK, B to the FK. Every element in here looks something like this. And let's see, does R commute with this? So what happens when we look at this element? Well, R commutes with A and it commutes with B, which means we can swap the R here, and we can swap the R here again. And we can keep doing that forever and ever and ever, at least as long as we need to, until the R eventually reaches here and cancels out with this guy. Which means it really does leave this element alone. It just equals to this stuff. Which means that R is also in the centralizer of the group generated by A and B, because it commutes with everything in that group. So that solves this proof, which is a useful proof to know. But we want to use this lattice somehow to figure out the centralizers of each element. There's a lot of elements in this group, so I'm suspicious. So here's the deal. Sigma is cyclic, so you know, this centralizes here, this centralizes here, this centralizes here as well. Does anything commute with sigma? Remember, this is the quasi-dihedral group we're looking at, right? Yeah. So in the quasi-dihedral group, we have this presentation. So is there anything that commutes with sigma? So let's figure out. Every element in the quasi-dihedral group can be written as sigma to the I, tau to the j. So what happens when we do, I guess, sigma to the I, tau to the j times sigma times tau to the negative j times sigma to the negative I. What happens here? We know how to commute sigma and tau, right? And so that means, what does this mean? I guess we can swap these two. But it doesn't quite work. I can't just swap these two. I'd have to swap these. And I'm sending sigma through j taus, which means it turns into sigma I plus 3 raised to the power of j times tau to the j times tau to the j minus j times sigma to the negative. Wait a second. This should be a negative I, shouldn't it? Yeah. Times sigma to the negative I. So this cancels, and we're left with sigma to the I plus 3 raised to the j times sigma to the negative I. So in total, we've got just sigma to the 3 to the j. And the question is this the same thing as sigma? So the question is, when is 3 to the j equivalent to 1 mod 8? Which powers of 3 come out to 1? That's a good question. I don't even know if there's a nice pattern. It's going to be very weird. Very weird. So let's see. What are the powers of 3? We've got 3, and we're working mod 8, remember. 3 squared comes out to 1. I see. So the powers of 3 cycle like this. 3 is an order 2 element working in Z mod 8 Z star. Okay, so as long as j is even, we should be good. So which is only equal to sigma if j is even. So the only things that commute with sigma are when there is no tau, which means sigma centralizes to itself. Okay, good to know. Wait, I don't know why I'm erasing that. Let's keep it. Okay, what are the other single element things here? Here's tau. What stuff commutes with tau? My suspicion is that sigma 4 is special and commutes with everything. So let's see. Sigma 4. Let's just take an arbitrary element. So sigma to the I, tau to the j. And then tau to the negative j, sigma to the negative I. What does this come out to? So what things can we swap? I suppose we can swap these. Ah, shoot. Thing is, we need to send 4 sigmas through j times. So it's going to be sigma I plus 12 to the j times tau to the I times tau to the negative I. Sorry, wait. Times tau to the j is what I meant. Times tau to the negative j times sigma to the I. So these two cancel, and then this I here cancels with this I. So we're left with sigma to the 12j, which is really sigma to the 12 to the j. But sigma is order 8, so this is sigma to the 4 to the j. And this should be sigma to the 4 whenever. The question is, when is 4 to the I equivalent to 4 mod 8? Well, what are the powers of 4 in Z mod 8Z? We've got 4. Then 4 squared is 16, which is 0. And then 0, and then 0, and then 0, and then 0. So whenever j equals 1, I'm confused. Maybe I did the swapping wrong. Let's do some casework. Yeah, that'll actually make life easier, right? So let's see. Let's see when we have sigma to the I composed. So something like this. This is obviously just going to be sigma to the 4 because it's I plus 4 minus I, which is just 4. On the other hand, what happens if we have sigma to the I times tau times sigma to the 4 times tau inverse times sigma to the negative I? So this time we only need to swap, once. Now, what was the rule to swap these two? The sigma becomes 3 times, right? So swapping these becomes sigma to the I plus 12 times sigma to the negative I, which comes out to sigma to the 12, which is in fact the same thing as sigma to the 4. So sigma to the 4 is special in that it commutes with everything, which is interesting. So sigma to the 4, because sigma squared does not commute with everything. Sigma does not commute with everything. Sigma to the 4, however, commutes with everything. So this guy centralizes all the way up here. Okay, so what does tau commute with? Tau is going to commute with its powers. So let's see. Sigma to the I, tau to the j, and then tau to the negative j, sigma to the I. Sorry, negative I. So this is going to be sigma to the I, tau, and then sigma to the negative j. And then we can swap these and get tau times sigma to the 3i. Sorry, that was a lot of scrolling. Sigma to the 3i minus j. What have I done? No, this is not a j. This is a negative I. Yeah, so this is sigma to the 3i minus I, which is tau sigma to the 2i. And this is going to be the same thing as tau whenever I is a multiple of 4. Yeah, because sigma has order 8. So whenever I is a multiple of 4, this disappears. So that's the stuff that tau commutes with. So tau commutes with... Hi, Aryan. Yeah, I'm going to finish like 3 more questions. And then I'll be done. These 3 questions here. I just want to finish this chapter. I'm so close. Right, so tau commutes with all of its powers. And then it also commutes with it commutes with sigma to the 4 and then sigma to the 4 tau as well, which means that this centralizes up here. Okay, what about sigma 4 tau? What commutes with you? Well, sigma 4 commutes with everything. So the stuff that commutes with sigma 4 tau is exactly the stuff that commutes with tau, which means this centralizes here as well. Okay, next up the question is, what commutes with sigma squared tau? This is slightly trickier. So let's see, does this commute with powers of sigma? We can, I don't know, we'll have to swap something. What do we swap? Because this is sigma to the I plus 2 times tau times sigma to the negative I. I guess we can swap these and get sigma to the I plus 2 minus 3i times tau, which is sigma to the 2 minus 2i times tau. And this should come out to the same thing as sigma squared times tau whenever I is a multiple of 4. Okay, so only sigma to the 4. What about when you have another tau thrown in, like this? What happens then? Well then, these cancel out. We're left with sigma I tau sigma 2 minus I, which is tau times sigma to the 3i plus 2 minus I, which is tau times sigma to the 2i plus 2. And of course this 2i section is going to disappear when I is once again a multiple of 4. So what does that mean? That means the stuff that commutes with sigma squared tau is all the multiples of sigma squared tau, and then sigma to the 4 and sigma to the 4 tau. So the powers of this and this stuff, which means that we are going to centralize here.